So Lisa is a member of that institute, and she works on hurricane research. She is originally from Michigan, and she earned a bachelor's from the University of Michigan and a master's from Florida State University. She will tell you more about her time here, and welcome, Lisa. Thanks.
So thank you for that introduction. Hi, I'm Lisa Pucci. I've been down in South Florida since 2010, beautiful South Florida. And since 2012, I've been with the Rosenstiel School as a research scientist. And when I found that my master's wasn't going to get me to where I wanted to be, I was given the opportunity to apply to the Ph.D. program. So I was accepted, and I am now in my 5th year of studying. So it's been an amazing journey, and I've gone through, you go through a lot of changes in 9 years, and it's, being here has been amazing, both professionally and personally. So on the personal side, we've gone through a lot of changes. My husband and I have just welcomed our first kid. She'll be a year old in February, our little Miami hurricane. And just being a new parent down here has been incredible, just from helping them navigate maternity leave to coming back and finding that work-life balance to just having the colleagues bring you some warm food when you don't think that you're ever going to get a meal or a shower again with a newborn has been incredible. So just thank you to everyone for that. And then professionally, I've been able to have a pretty unique experience because while I am employed by the Rosenstiel School, we also have this Cooperative Institute where we partner with NOAA laboratories, including the one right across the street, the Atlantic Oceanographic and Meteorological Laboratory. And through this partnership, I've actually been able to get my dream job. So I am a hurricane research scientist. And with that, I get to study hurricanes, and one of the ways that we study hurricanes is by flying into them. So every year, I get to fly into hurricanes. So this is actually some imagery from last year's hurricane that you will remember very well, Hurricane Irma. So that's actually the eye of Hurricane Irma, as it was a Category 5 off the coast of Cuba. And we have all this instrumentation on the plane. So in the lower right-hand corner is a radar snapshot of what it was like. And we collect data when we're on this plane and send it off in real time. And so that's my colleague, and he is quality controlling this data to make sure that we give everybody the best picture of what is happening right at that moment. And we fly into hurricanes because this is the best data that you can get. We do have satellites, but if you really want an accurate measurement of what's going to happen, they put us in these planes and they send us out there to get the data that they need. So these observations are collected and we send them off in real time. We send them to the National Hurricane Center to give them the best picture of what's happening right at that moment to help make their forecasts better. We also give this data to modeling centers. So you might see those spaghetti graphs on the nightly news. They're getting some of that data to run some of those models from our plane. And finally, this data is public. So we provide the data to the broader research community, and they use that to help understand processes that we don't quite understand very well, and they're trying to improve our understanding so we can improve our forecast, which as residents of South Florida, I'm sure you approve of. So one of my particular interests is we treat this plane like a flying laboratory. So we have instruments that we regularly collect data from, but then there are opportunities for us to try new things or fly in different places in the storm. So my interest is with a new instrument called a Doppler wind LiDAR. It's a laser, so I'm not trying to give the hurricane, it's a low-powered laser. I'm not trying to give the hurricane LASIK eye surgery or anything. But it does collect the winds, either below or above the plane, depending on where I point it. And we had never flown one of these on this aircraft into an Atlantic hurricane before. So part of my research was to just get this to work, which you can see me trying to do in the right-hand panel. That's the machinery on the inside of the plane, and then on the outside of the plane, it kind of juts off the back of the plane, and you can move it, that barrel twirls around depending on where you want to point it. So our first objective was just to get this, this instrument to work, which actually is not as easy as that sounds. It took us about a season to get all the mechanical bugs worked out. But we got it working, we got data, but then once you get data, how do you know that it's good? So we had to do a validation study. We had to compare it to other wind observations and make sure that everything was comparing well and that we could trust the data. And thankfully, we got that. So trust me, that graph means that the data's good. And finally, we wanted to make sure that we were getting useful information, because you could get useful data, but if you have other instruments on the plane and they're already getting the data, then why would you have a repeat instrument? And it turns out that we get a lot of data that is brand new. So we're able to observe parts of the hurricane that we weren't previously able to observe, and that's helping us give this more complete picture that, you know, the forecasters at the National Hurricane Center and the modelers and the research community all want. They want a more complete picture of what's happening in this hurricane. So my next steps are to see what this data is telling us in those areas that we haven't previously been able to observe. So that's all well and fine. Everybody, you know, came here to hear about science, but the question that I get asked the most is, what's it like to fly into a hurricane? So I brought a video, and I'm going to make sure that this video isn't too loud, because you don't need to hear how loud it gets on this plane. It's a 4-propeller prop plane. It gets pretty loud. So this is in Hurricane Lane, which was a Category 5 storm off the coast of Hawaii this past year in 2018. It's starting off in the eye wall, and every hurricane's different. You get some big bumps in the eye wall. Sometimes the whole storm is just like driving down a road with a ton of potholes, and you're just constantly bouncing around. And occasionally, it's nice and smooth. This one had several bumps, and then once you got through those bumps, you got rewarded with this gorgeous eye and a sunny eye, which is not something that you see all the time. And actually, you could see all the way down to the surface where these waves are just crashing into each other below the plane. So that isn't something that you often see, but when you do see it, you pull out your phone and start recording. So, you know, it's an incredible experience. I learn something new every time I get in that plane and fly, and it's been incredible. So with that, I will leave it right there, and thank you for your time and attention.
All right, well, we have great students, okay, courageous students at Rosenstiel. Thank you, Lisa, again, very interesting. Well, so as you have heard already from Josh, I'm sorry to let you know that Craig McLean could not make it this evening, and we are sorry that that is the case. I believe he committed to come back for next season in January. So it's just a slight delay in his presentation. Hopefully then the government will be reopened. But you're not going to be shortchanged, because this evening I am truly pleased, okay, to introduce a great colleague, Professor Ben Kirtman. I have a long briefing to make here. His career is, one of the most successful career of people in academia. But let me first start by saying really who Ben is for this school and for the university. You know, as a dean, there are very few people, very few faculty that you can always rely on. You know, they are the perfect faculty. They are very productive, excellent teacher. speaking at every opportunity, and then sometimes they are also willing to do anything that you ask them to do. Ben is one of those very, very few faculty that we have, and I am extremely proud and delighted to have Ben as a colleague and as a friend. Ben has served already for the school as an associate dean for research for a period of 3 years, and he remains a personal advisor and consultant and confidant on many of the issues that we are trying to do at the school. He is, as I have mentioned before, the director of CIMAS, that cooperative agreement that we have with NOAA, which is producing right now about 40% of the $55 million research that we operate every year on about 200 research projects that we have. So this is a huge responsibility, with a huge responsibility in terms of the faculty that are involved in that, as well as the graduate students and the postdoc that are part of this center. So Ben is leading that activity. And as that was not enough, he's also one of the director of the Center for Computational Science at the University of Miami. So thanks, Ben, for agreeing to do that. Let me mention kind of the more traditional background for Ben. So he started from a BS in mathematics at the University of California, San Diego. I'm not going to mention the time because that will make him a little bit older than what he looks like. So, but that was kind of a while ago, and then he got his MS and a Ph.D. at the University of Maryland. After that, he worked in an institute, a quite famous institute in climate, which is called the COLA, the Center for Ocean, Land, and Atmosphere, in Maryland. And after that, he worked as a George Mason University as an associate professor tenured, and he was recruited by Rosenstiel in 2007. So, you know, I think that that was, as I have emphasized already, one of the best recruitment that the school has made. Ben is a recipient of multiple awards. And just this past year, he was elected a fellow of the American Meteorological Society, which is a kind of, you know, very prestigious recognitions for the scientists that we have. He received also, I mean, a variety of different recognitions, including our Provost Award, which is given to one faculty every year around the university. And I believe that he receives that in 2017-18 as well. He has been recognized at different universities, different organizations, including the Stony Brook Lecture, the Robert S. Distinguished Lecture in recognition of outstanding contribution to atmospheric science. Internationally, Ben is also extremely well known because of his participation and leadership in the World Climate Research Program. Again, one of the important programs that is the organization of the World Climate Project. And he was, in fact, one of the chair and the organizer of one of the very famous Intergovernmental Panel on Climate Change, the IPCC, the chapter or the working group number 1, which is providing the scientific basis for the entire IPCC. Ben has served also in multiple roles, in addition to what he has been doing at the university and the school. One of them is the executive editor of Climate Dynamics. He has been an editor, which is another way of the community to recognize the expertise of a great scientist, is by relying on them, by giving them this job that consists of evaluating the work that is done by all the scientists in the field. So it's extremely prestigious to have been asked and have been served on the climate dynamics and the Journal of Geophysical Research. He has received the grants from multiple organizations and agencies, which is yet again another way of being recognized scientifically. And that includes the National Science Foundation, the Department of Energy, NOAA, NASA, the Office of Naval Research, and he's one of the leaders in multiple experiments. He has published more than 140 papers, and that's, again, kind of a very impressive numbers. And as I have emphasized, one of our most talented faculty and one of the best colleagues that we have. So Ben, thank you so much for jumping in and agreeing to do that for us, and welcome.
Thanks, Michael. Thanks for that very nice introduction. Someone's going to make something good happen here. So the first thing the first thing I wanted to say is that the first thing I want to do is just lower expectations as much as possible. So first, there's no baby pictures. I can't compete with Lisa Bucci's daughter. I'm not Craig McLean, not by a long shot. I work a lot with Craig through the Cooperative Institute, and so I strongly recommend when he does come next year that you attend. He's a great guy and honestly really interesting. Oh, I'm locked here, so I have to. Okay, something good will happen. So the other part of lowering expectations is some of you might have expected me to talk about climate change. I do a lot of work in climate change, but I'm actually going to talk mostly about a significant different part of my research portfolio. And that really just, even though climate change is in the background of this portfolio, it really focuses on predicting hazards, environmental hazards, from 3 to 4 weeks from today out to a month, a few seasons, maybe even out to 5 years. And this sounds like a little bit of a crazy idea. So I have to spend a little bit of time convincing you that perhaps it's not a crazy idea. There is something we can do. And we're making a lot of progress, but we have a lot more to do. So that's kind of what I wanted to talk about today. A big part of our success in doing that is our relationship with NOAA. I'm going to talk about in particular two special, that's my email coming in. Right. And when that's on at home, my wife says it's dinging all night long. Anyways, so I'm going to talk about two projects that are very, very near and dear to my heart, and I'm going to apologize at the outset for my passion for these two projects. One of them is called, and I'll describe it to you, it's called the North American Multimodal Ensemble. This is a project that the University of Miami leads. And it's a project to improve, prediction of droughts and floods a season, a month, or even out to a year in advance. And I'll show you some success stories, and I'll show you some things that need improvement. Now, the reason this project is so exciting to me is it's now an official operational product of the federal government. So, okay, you're sitting in the back row, what's the big deal? What's the big deal? To a scientist, scientists like me, this is a huge accomplishment. So the NOAA has a congressional mandate to produce forecasts on time, in real time, all the time. Failure is not acceptable, cannot happen. It's against the law. They're relying on us to produce the backbone of those forecasts. That's a huge responsibility, and it's a huge honor that our science has led them to believe that the methodology we have in place is the way to do this. And they continue to ask us to lead that. And we've been doing it operationally since 2015. So this is, in my heart, this is like, wow, that success. We've beaten back this problem. And indeed, when I recruit graduate students and I have a portfolio of projects, and I ask them, what do they want to work on? They all want to work on this NMME project. By the way, I say NMME really fast. It sounds like I'm saying enemy. Okay? I assure you it's not my enemy. Anyways, so this project I'm really, really proud of. The second project I'm going to talk about is called SubX. Okay? And so we have to put an X on everything in meteorology because we have to tell the world it's an experiment. So SubX is an experiment, and it's predicting on higher frequencies, a little bit shorter frequencies, more frequent initializations, and I'll explain what that all means. But this project was funded, and we were asked to lead it because of our success in NMME. It's not operational yet. It's only 3 years old. We don't know if we're going to reach that hurdle that's required in order for NOAA to trust us to continue to make those forecasts to improve what they release to the public. But that's our charge. And I'm going to talk about these two projects. And then I'm going to talk about how we're going beyond those timescales, how we're going out to decades, and how we're developing new tools to do that. So these projects, while the science we did to support these projects to me, is old. The operationalizing of it is really exciting, and it's these new tools to make those products better is the work that we want to do in the future and continue to do. Okay, so let me just go through a little introduction. So this is, I couldn't get an updated version of this. This is always a little bit behind. I couldn't get the updated version because of the government shutdown. The government, of course, keeps all these statistics for natural disasters. This is just from January through September in 2018, and this is only the events that the costs have exceeded $1 billion. That's with a B, $1 billion. So, this is a great motivator. If you can predict just to reduce the cost a little bit, 10%, 20%, so you can reposition equipment or warn people to get out of the way or whatever it takes, you can save an enormous amount of money and save lives. So you can see why graduate students want to work on these projects. When you're a graduate student, you want to save the world, right? Yeah, we make sure they're jaded later, don't worry. So this is a recent picture, and part of the reason why I remember this storm is it was a storm that happened on my mother's birthday. My mother was born on January 9th. I'm not going to say what year. My mother was born on January 9th, and this is in Montecito, California. It's not too far from where my parents still live. We don't live in Montecito. Montecito is where Oprah lives. So we don't live in Montecito. But anyways, this is a place, there's this beach here. It's called Butterfly Beach that you can sort of see the hint of in the second picture. And, when I was late in high school, there was some question of whether I was going to actually make it to college or just turn out to be a beach bum. But this picture was taken on January 25th. It's the same street, and you can see the muddy mess. A number of people died in Montecito during these mudslides. It was really quite bad. A friend of mine works for the homeless community in Santa Barbara, and was very anxious to get forecast information about what people were talking about a few weeks in advance, a few days in advance, because there were some concerns about serious mudslide risks. Those mudslides, of course, happened because of the fire. Right, so all the biology, all the plant life holds the mud on the hills, and when you have a fire, then you lose that and you get those mudslides. It was really quite serious. There's a lot of very scary photos that I'm not showing you. So I want to talk about it. I'm going to actually show you an example where we successfully predicted that the chances of this happening. Okay, so the question my whole career, a big part of my career anyways, is based on can I predict hazards weeks or months in advance or years, decades? Can we predict those? And of course, a lot of people say, well, you can't predict the weather much beyond 10 days, so what are you doing? This sounds like the Farmer's Almanac. Sound like a snake oil salesman. And so I want to show you I'm sure everybody in the room knows everything about nonlinear dynamical systems and chaos theory. But I just want to remind you of some of that theory very briefly. So I'll show you an example. It's a nice, very simple example you can play with at home when you want. And then I want to talk a little about, so why do I think I can predict beyond 10 days? I want to talk a little bit about that. And one of the key elements, one of the key things to think about is there's stuff that happens in the climate system that is relatively slow. Slow stuff in the climate system. Sea surface temperatures in the tropics, for example, are a great example. And I'm sure a vast number of you have heard of El Nino. Anybody raise their hand that hasn't heard of El Nino? Nobody, right? So everybody's heard of El Nino. El Nino is an enormous source of this longer-term predictability, and it's driven by sea surface temperatures in the tropical Pacific. So there are things that happen in the climate system that allow us to predict phenomenon beyond the weather timescale of 10 days to 2 weeks. So we're going to tap into that. I'm going to explain that a little bit. But this should also be sort of intuitive to you, right? Winter weather in Miami is quite a bit different than, summer weather in Miami. So you know that what's happening in the climate system affects the weather. So if there's something else on top of that, like an El Nino, maybe we can predict how that might affect the weather. So we're going to talk a little bit about that. And I'm not, in fact, I still occasionally get these phone calls. I'm getting married January 17th, 2023. Can I have an outdoor wedding? And, I say, well, that's winter, tends to be drier, so, there's chances you might be able to. But I'm not talking about predicting the weather on any individual day, not this sort of deterministic, it's going to rain or not rain on January 27th, 2025. What I'm talking about are changes in the statistics of weather. So can I say something about next summer? Is the hurricane activity going to be greater than normal next summer? Not that there's going to be hurricanes. I can tell you for pretty much certain there's going to be hurricanes. But are there going to be a lot of hurricanes or less hurricanes? Those kinds of things. Now, one of the other key concepts that has to go into this is this notion of ensembles. And it sounds very, very jargony. And the reason I have to use ensembles is because I can't forecast a specific event that's going to happen 175 days from today. I have to tell you about probabilities. And how do I formulate probabilities? It's a little bit like gambling. If you're playing the roulette wheel and you want to know what's the probability of 27 red coming up, you're going to play the wheel a bunch of times and calculate how often 27 red comes up. But if it's a good wheel, we can actually figure that out without running the wheel. But you get the idea. You have to do lots and lots of experiments to estimate the probability. So we have to do ensembles to estimate the probability. Now, there's a very interesting subtlety here. Because the hard thing is, how do you decide that, when I make a probability, that's a good forecast, that's useful? I'm going to talk a little bit about that too. That's a really tricky part of this endeavor of making hazards forecasts. Okay, so let's play with chaos. There's fun with PowerPoint. I figured out how to do the wobbling thing. I was pretty excited about that. So there's my butterfly. That's, of course, a real picture of a real butterfly. For those of you that haven't seen this before, that's the so-called Lorentz butterfly. That's from nonlinear dynamical systems theory. It's chaos. That's why the butterfly effect came about. Very nice, beautiful picture. This little simple equation, right? This little simple equation is chaotic. Okay? It's chaotic. And just a really simple example of this chaotic system is I run it twice, an ensemble of two, with a teeny tiny difference. A teeny tiny difference when I first started, right? 0.5 and 0.5001. Then you just apply the formula, you go forward, you march it forward, you get a picture that looks like this. Right? So this is, the first is doing this, 200 times, with that initial state, that 0.5, and this is doing it 200 times with 0.50001, out 200 steps. Right? And so if you look at the beginning, they're right on top of each other. Pretty close. They stay close together. That's what your intuition would tell you. But if you go out further, they start to look a lot different. And that's why we believe the atmosphere is a chaotic system. The equations that govern the atmosphere are only slightly more complicated than this equation, only slightly, but the phenomenon is the same. They're chaotic. You go out to significantly far away, the two solutions deviate. So if I want to talk about a change in the statistics, I'm going to do lots of little tiny perturbations, and I'm going to run it over and over and over again, and I'm going to check to see if the statistics are changing, not whether I get a particular event. It's just a plot of the difference of those two. And so this is the same idea, Exactly the same idea, but with a real model, not that toy model. This is from the European Center, one of the better institutions like NOAA, making hurricane forecasts, and this is from Superstorm Sandy in 2012. And tiny perturbations to the initial condition. They start out, they stay close together. The colors denote each day, so the red is the first day, the green is the second day, and I can't tell the difference between the blues. I have a little bit of color blindness. And then you get out at the end there, and they're quite a bit different. And to humans, of course, to a meteorologist, like, oh yeah, it's pretty close. But to humans, if you live in Virginia, it's a whole lot different forecast than if you live in, say, Rhode Island or Connecticut or something like that. Very different forecast. Okay. So here we are. So this is a schematic of what's going on in my brain about this. We have these weather forecasts. They start out at the very beginning with very good skill. We forecast the weather a few days in advance really well, and that skill falls off, right? And I'm not going to talk about that anymore. I'm done with the weather. What I'm going to talk about are the other curves. So then there's this sub-seasonal time scale. 2 weeks, 3 weeks, 4 weeks. And you can see the skill starts off poor. Starts off poor. So figuring out how to use these forecasts and making them useful is tricky business because the skill is low. But if you do it over and over again, it's like playing with loaded dice. You're going to make money. And then the seasonal forecast, that's the NMME project, right? That's my, it starts out with better skill. It's, fair. It's not as good as a one-day weather forecast, but there's a lot there. And I'll show you some examples of that. And then out to decadal timescales, that's open turf. We don't know how skillful that is. We're still working that problem. That's going to be a while before we have a lot of confidence in decadal forecasts. Okay, just a quick example. Apologize for the somewhat blurry picture. This is what's called the Madden-Julian oscillation, sometimes called the 30 to 60-day oscillation. It's an oscillation in the tropics. All I mean by an oscillation is part of the tropical system is somewhat wetter than normal, and part of the tropical system is somewhat drier than normal. So the green colors correspond to being wetter than normal, and the brown colors correspond to being drier than normal. And you can see by the arrows that I'm trying to say that this thing is moving across the tropics, across the globe. And it has, this time scale of several days to a few weeks. It's the Madden-Julian oscillation. So what? The so what is, if you're in what's called the easterly phase, that dry phase where actually the atmosphere has lots of descending motion, you can see a lot less hurricane and tropical storm activity. So if I could forecast that 3-4 weeks in advance and tell you we're going to have a big lull 3 or 4 weeks in hurricane activity, you can start thinking, okay, this is an opportunity for us to think about how we're positioning resources, how we're getting ready for the rest of the hurricane season. Or if I tell you 2 or 3 weeks in advance, maybe 4 weeks in advance, that we're going into that westerly phase and the probability is a much more active period, you're going to reposition resources to make sure you're prepared. Very useful information. So if I could predict that Madden-Julian oscillation, that could be helpful. So let's talk about El Nino as another source. This is on longer timescales. This is now on months or seasons. This is a picture, this picture of El Nino. I was famous for 5 minutes during the 1998 El Nino. And the reason I know I was famous is Polish Newsweek called me up for an interview. So I've been published in Polish. Okay, so this is a picture of what the El Nino looked like in 1998, and then the picture below that is the La Nina that happened to happen about a year later. And La Nina, you can think the temperature, that's a picture of the ocean temperature anomalies, how it deviates from normal. So if it's blue, it's relatively cold, and if it's red, it's relatively warm in the tropical Pacific. Okay? And that affects how the rainfall distributes in the tropics, and then ultimately around the globe even. And so we did an experiment, a natural experiment to do. This is looking in that the rainfall in that black box on each panel. So in the red squiggly lines correspond to the rainfall during the El Nino, and the blue squiggly lines correspond to the rainfall during La Nina. Yay, another email. So what you can see is as you start the forecast, all these experiments, boy, those squiggly little lines, the red lines and the blue lines, stay on top of the black line. They're all close together. That's what I mean. That's sort of the weather forecast. But when I go out to longer time, many more days, they start to wiggle all over the place. But you can tell by eye, just by looking at it, the statistics of the red curves are very different than the statistics of the blue curves, despite being in exactly the same place in the globe. That's what I'm trying to predict. I'm trying to predict a change in the statistics. And in order to robustly detect that change in statistics, I need to do ensembles. Decadal timescales, there's this phenomenon called the Atlantic multi-decadal oscillation. It has multi-decadal timescales, hence the name. It looks something like that, warmer throughout the northern Atlantic Ocean than normal. And we can look at how it oscillates in time. And we can also in the black curve, so the blue bars and the red bars are it going from positive to negative phases. And then the black curve is showing you hurricane counts. And so you can see there's a loose relationship between this Atlantic multi-decadal oscillation and total hurricane counts. So if I could predict, what that AMO thing is doing a few years in advance, those reinsurance guys might be interested in me. I just like this picture. It's kind of cool looking, right? We need ensembles. Okay, so how do we make a forecast? And so obviously we need observations. And what I want to emphasize is that's a big part of what Rosenstiel does. We develop state-of-the-art observation systems. We go out there and do those observations. I don't do any of that. Those observation guys barely want to talk to me because I'm a computer modeler, but that's okay. But I know precisely how important it is that they do what they're doing. Because I couldn't figure out, there's no way in the world I could make a forecast if I don't have a picture, an image of what the climate system looks like at the moment I want to start that forecast. I can't start from nothing. I can't start from climatology. I have to start from an image of what the climate system really looks like on that day. I need those observations. They're critical. And indeed, the government shutdown is putting in this on-time, real-time, all the time, is putting us in a tough spot. We're getting a little concerned, and I'll explain that in a minute. We need a prediction system, a computer model, right? And so I'll show you a picture. How do you describe a computer model, right? But I'll give you some kind of picture. It's not trivial to figure out how does one explain a computer model. It's basically a recipe. It's just a really darn complicated recipe to figure out how to go from here to there. It's a formula, but it's really, really complicated. Indeed, the climate system is so complicated, we don't even know how to write down an answer to those set of equations. We don't know how to solve them, so we have to use a computer to do it. And then we need to figure out how to insert those observations into the model to start the forecast. And that's a whole separate field all by itself called data assimilation. That's kind of what Lisa works on. And I should take this moment to pause and say something. Lisa does lots of experiments. Lisa Pucci does lots of experiments, but she is also an experiment all by herself. What I mean by that is Lisa's the first of, I hope, to be a train of scientists that are Cooperative Institute employees that continue on and get PhDs at the University of Miami and then become the stellar workforce for NOAA. And I see that happening with Lisa. So we're really, really proud of her. The experiment is turning out really, really well. So here's my cartoon of a climate model. So you have to think we have to put this sort of grid on the Earth, and then these this is just some image of some of the equations we solve. We've been all working with those since we're in the 6th grade, so no big deal. I don't need to explain them. The ones I have up there are just for the atmosphere, but I have to have a whole set for the ocean. I have to have a whole set for the sea ice. I have to have a whole set for the land. Our dean is one of the world's leading experts on how the land and the atmosphere interact. We have to have guys like him involved. And then there's another cartoon there with volcanoes and rain and clouds and you know, soot and trees and all these things. And all these things are important in how they interact. So it's trivial stuff. Easy, no problem. I like to think it's actually harder than rocket science. Okay. So I've got my initial conditions. I've got those observations. I figured out how to insert them in the model. I've got my model. I march it forward in time. I do it over and over again because I know I have to make a probability forecast. And so here's a cartoon of what I'm thinking about in my head. The red curve would be just taking one of them. And the blue curves are all a bunch of ensemble members. And so they sort of give a thing, a blob. A blob. That's the forecast. Now in this picture, what's really, really important is the blob of my forecast is smaller than the blob that's climatology. If they were identical on top of each other, I'm useless. What do you need me for? Just make the forecast climatology. So I have to do, so this is the tricky part. I have to introduce a probability forecast, but it has to be a forecast that has actual information that someone can do something with. It has to occupy a space that's smaller than the entire climatology. Tricky stuff, especially when I'm going to show you the next picture. What if what happens actually lies inside the climatology, which it has to because that's climatology, but it's outside my narrow blob? This is bad. Okay? This is a bad forecast. And just in case you didn't hear me, bad forecast. Okay? This would be a good forecast. What happens in observations is in the blob that my probability of forecasts do. And so that's the tricky part, is designing these systems that have the appropriate resolution, if you will, to capture something that's a probability, but is narrower than climatology. And it's much harder than I would have thought. It's very humbling, let me be clear. So part of doing that is we've talked a lot about this initial condition uncertainty. I tweak the initial conditions. I do it over and over and over again. The big innovation, the big thing that we're adding to the mix here at the University of Miami in both of these projects is we're leading the implementation of using multiple tools to do that, multiple models. And that's because models are not perfect. They're far from perfect. And so we're taking advantage of all those imperfections to make sure our blue blob captures the observed event, but not goes all the way out to climatology. So that's the big innovation here in a nutshell. So here's NMME, not my enemy. You can see it's up at the Climate Prediction Center. It's an official operational product. We've been doing this since 2011. We've been doing it operationally since 2015. The head of the National Weather Service at a retirement party when we were in 2015, someone else, not my retirement, or somebody else's retirement party, asked me, what am I going to do if you get hit by a bus, Kirtman? And part of it was a joking question. He's a really nice guy. His name's Lou Uccellini. He's a brilliant scientist. It was a joking question, but he had a real point. He's relying on us. He's relying on us to be on time, in time, all the time. He's relying on me. Do I have backup systems? Do I have things in place so that if I did get hit by a bus, sorry, honey, my wife's over there, that someone would, make sure this continues to happen. I had to jump through all kinds of hurdles to convince them that I thought about the eventuality of what could I do if, for some reason, Hurricane Irma came through. and I had to relocate to Atlanta. How was I going to get my forecast in on time? I did. So I had to convince him I could do all those things. There's only one thing that I told him I can't fix if there's a government shutdown. So this picture is precisely why this NMME project has been funded now out till 2022. And it'll probably be renewed again out to 2025. This picture, and it, you look at that picture and you go, boy, Ben, what are you all excited about? There's a little bunch of colored squares, okay? And I know you're all very familiar with this thing called the rank probability skill score. Very important. And I know you've been worried about that your whole life. This skill score is a little bit like asking the question, did the green dot in the previous plumes, did it lie in the blue blob that I predicted, or did it lie outside the blue blob? Okay? So it's asking that question, am I getting that probability right? That's the skill score. And blue is bad. Blue is so bad that I would be better off guessing. I would be better off with the Farmer's Almanac. Okay? So that bottom panel, that was the official forecast that NOAA had been issuing before the NMME project. Before the NMME project. The top panel is after the NMME. And note, I'm sure it's no coincidence whatsoever, that we do better in South Florida, the whole Southeast. I'm sure it's because we're here. One of our big success stories was actually in 2012, before we were operational. We were still doing it in real time. We were being tested. Can you guys actually do this? And there was a very serious heat wave in the Midwest. In July of 2012, 82 people died, I think. And there was this massive derecho, which is a sort of line of thunderstorms, very severe. This is 1 month in advance. The top row is showing you what happened in standard deviation. And so it's a question of how extreme. So, for example, 2 standard deviations is way out in the tails. It's rare. 3 standard deviations is really rare. And so you can see the temperature anomaly in the upper panel for the observations is like 2.5 standard deviations. That's a very rare event. A very rare event. And then the forecast in the bottom just below that, that's the probability of an extreme event. It's the probability of an extreme event. And so had we been operational, had the forecasters been using that, we'd like to think that maybe people would have been able to prepare for that. Cooling centers would have been fully hardened and ready to go so that 82 people wouldn't have died from heat stroke. The NMME system is now a critical part of NOAA's operational hurricane seasonal outlook. They make this forecast every season. This is a critical part of our interaction with and through the Cooperative Institute. Why it's so important for me personally to have this interaction with the Cooperative Institute. Not to mention I get to see the seasonal outlook a few days before you guys do. So the only thing I want to point out in this picture is these are individual model forecasts, and in the oval there that I've circled is the NMME forecast. And so for correlation, you want a higher number. For the RMSE, you want a lower number. And you can see, of course, we put first for the NMME system over any of the individual models. And then this is just, this is now in the operational phase. This is the 2017 Atlantic Hurricane Outlook, what was forecast in August, the August update, the May outlook. The climatology is that seasonal average, what we typically expect, and then, of course, what happened. And the NMME is the major informer of those official outlooks that NOAA makes. So here's your actual forecast. So we were able, despite the government shutdown, we were able to get our official NMME forecast in by January 1st. It was a little bit tricky. I'm not convinced if the shutdown continues into February that we'll be able to do it again, but we did. So here's your forecast for and it's a probability forecast of what's going to happen to sea surface temperatures February, March, April, and a rather boring outlook for rainfall over the U.S. Not much happening. Perhaps in the Pacific Northwest, it's a little bit drier. It looks pretty good chances of wet in Alaska. But that's the official forecast. Sometimes they're boring. What can I tell you? So let me drill down into the faster timescale, the shorter timescales, that sub-seasonal timescale, that 3 weeks, 2, 3, and 4. This is the new project. So we're very excited. You're always chasing the latest shiny object. So this is a new one I'm very excited about. It's not operational. It's still in its experimental phase. It took us from 2011 to 2015 to convince NOAA that the NMME system should be operational. It's going to take even longer in this case because this is even harder to coordinate because it has many more moving parts. But that's my picture from Montecito, California. From January 9th, the storm actually hit January 9th. And this is the rainfall forecast that we made. It was 3 weeks before January 12th. So it was the week ending January 12th. And of course, the greener or bluer colors were for heavier rainfall. Okay, so if I had stopped there, everything would be perfect, right? We're perfect. Nothing to fix. I guarantee you there's lots to fix. In fact, it's a little embarrassing what's there to fix. So this is a picture of that ranked probability skill score that I showed you before. I said is really important. And everywhere it's blue, it's bad and really bad. And everywhere it's red, it's pretty good. There's an awful lot of blue on that map. Everywhere it's blue, I would be better off using the Farmer's Almanac, better off guessing. Okay, so there's some challenges, some real challenges. One thing I noticed when I saw this picture is it's kind of happening in an interesting place. It's happening where ocean eddies are really important, where the Gulf Stream is, where the Kuroshio in the Pacific, and in the Southern Ocean, there's this really rapid currents in the Southern Ocean and lots of eddy activity. So very small scale, 10 kilometer, 20 kilometer, 50 kilometer variability in the ocean. And for some reason, we're not capturing that in our current generation of models. So the master of the obvious that I am, I said, well, maybe we should capture those eddies in the ocean. Maybe we should capture them. So this, with climate modelers, you got to be really, guys like me, you got to be really careful because the previous model is always crap, and the current model is spectacular. And if they allow me to speak again, I'll guarantee you I'm going to come up here and I'm going to tell you the new model is spectacular. The bad, So, but anyways, that's the traditional model. That's the model that's operational. That's a picture of what the ocean's surface currents surface kinetic energy looks like. And in a minute, I'm going to try to convince you that doesn't look like nature very much. This is a new model that we've been developing here. And the hard part is to figure out how to use it in forecast mode. But this is the new model we've been developing here, and I think it looks much more realistic. And the question is, does it produce better forecasts? But you can see it has the ribbon of the Gulf Stream. It has loop current eddies that get out into the middle of the ocean. So we think that's a much better model. And so here's another picture. That's observations. That's what the traditional model looks like. So you can see it's missing. This is sea surface temperatures from satellite observations. Red, warm, blue, cold, pretty obvious. That's from that traditional model. And you can see it doesn't really capture that front very well between the warm and the cold. That's the Gulf Stream. And then when we put in our high resolution model, you can see it really does capture that front very nicely. Okay. So I'm going to lower expectations one more time. Lisa showed, the coolest movie, right? Flying into a hurricane. As a climate modeler, what am I going to show you? Pictures of me typing in my keyboard? What am I going to show you? There's the computer lights blinking. Just a tremendous, whenever I follow someone showing a cool video, I just have this tremendous sense of inadequacy. So, but I'm going to show you a really boring movie. okay? But I promise you I'm going to follow it with, in my mind anyways, it's an Academy Award-winning movie. Okay? So I'm going to start with the boring movie. So this is just ocean currents in that standard climate model. By the way, on my computer, the resolution is so much better. The pictures are nice and crisp, so I'm just reporting. But anyways, not much is happening. This is 20 years going by in a simulation. And you can barely see, the current seems to change a little bit. You don't see any loop current eddies. Like, what's the Gulf Stream in that? Not very exciting. That's the standard one. Okay, boring, right? It was only 20 seconds, so you survived. Here it is, Academy Award winner. Hold your applause, though. Look at that. Look at those loop current eddies. In this simulation, hurricanes can get trapped in those loop current eddies. The core in the Gulf of Mexico, the core of those loop current eddies is really warm. The sea surface temperature is really warm, and we actually see the phenomenon where hurricanes get trapped inside those loop current eddies. It's a phenomenon that happens in nature, but just wasn't available in those older models, that older model, even though that model is operational. So that's really exciting. Okay, almost done, folks. Here it is. Here it is. This is that infamous ranked probability skill score. And I'm going to tell you in a second why I keep banging on that ranked probability skill score. So here's the ranked probability skill score from an overlapping set of forecasts. Same set of forecasts, same set of initial conditions that started off. The top is the traditional model, and the bottom is this new model. We're really quite pleased with those results. We haven't introduced tremendous skill. We haven't done that, so there's work to be done. But we've gotten rid of just going with the Farmer's Almanac. Okay. One thing I want to say is, this was a really humbling experience for me to learn this, and that you learn this by participating in operational forecasting. And it's if nobody uses the forecast, it has no value. If nobody looked at this stuff, then it's of no use. It's no value to anything. So how forecasts are ultimately used to support decisions is really, really important. Really important. So that decision support aspect is something we have to think about very carefully. And the reason I focus on this ranked probability skill score is if you put an economic model to play, a cost-loss economic model, that you include the cost of action versus the expense of inaction, right? If you include that, RPSS, improving the ranked probability skill score, directly leads to improvement in economic value. Directly. They're isomorphic, same thing. So that's important. So we really need to shoot for improving the ranked probability skill score. To do that, this is my editorializing before I finish, you really need to interact with the people that are making decisions. Because how you figure out how you're going to do your forecasts, what variables you're going to forecast, how many, if your variable happens to be a squared quantity, I know that sounds like a funny thing, then the number of ensemble members you need to detect a change in the statistics goes way up. Goes way up. So I need to know what someone needs information on. I need to know what thresholds they're worried about. So you need to interact with the people that are actually making decisions. We don't do that. Or we don't do that very well. That's something that we need to figure out how to do a better job with. With that in mind, I'm going to conclude with the actual forecast. Again, the one that says NMME is the one I've already showed you. This is the rainfall forecast for February, March, April. It's a probability forecast. Looks wet in Alaska. Not much happening here. Sorry. This is the sub-X forecast for 3 to 4 weeks from now. And so you can see that sort of dry signal is also in the near-term forecast for the Pacific Northwest. And a lot of the wet in Alaska is also detected. And there's a little bit of signal, a little bit wet signal in South Florida the next 3 or 4 weeks. And I put this up here, and I hope you've all taken a mental picture of this. So at the next Sea Secrets, or you can tell me, that was a total crap forecast, Ben. Thanks. I'll stop there. And you're welcome to leave, but if you have any questions, I'm happy to.
Thank you.
Joyce.
You were great.
Thank you.
How does this filter down to our meteorologists on Channel 10 or 6, whatever? Does this filter down to them?
Some of the more experienced forecasters, yes. So I do know, particularly in California, these sub-X forecasts, because they really worry about these systems that come off the coast, they do pay attention to the sub-X.